Have you ever really thought about what happens when you flick on a light switch or turn on the tap? It feels like magic. But behind it all are these massive, invisible networks, industrial control systems. And today, we're going to pull back the curtain on the technology that acts as the brain for pretty much our entire modern world.
And I'm not just talking about a single factory here. We're talking about pipelines that stretch across continents, power grids that light up entire nations. The scale is just mind-boggling. So how is it even possible to manage all of that? Well, the answer lies in this incredible technology that acts as the central nervous system for all our critical infrastructure.
So, here's our roadmap for today. First up, we'll get right to the heart of what a SCADA system is. Then we'll figure out how these systems talk to each other across huge distances. After that, we're going to dissect a real-world utility grid to see it all in action. Then we'll get into the really tricky modern problem of connecting the factory floor to the corporate office. And finally, we'll look at the blueprint the pros use to make sure it all runs safely.
All right, let's jump right into our first section. We're going to get a handle on SCADA systems. So what exactly is this brain of the operation?
You know, the name actually gives the whole game away. SCADA stands for Supervisory Control and Data Acquisition. Think of it like this. The data acquisition part is the system's eyes and ears. It's constantly pulling in information from thousands of sensors out in the field. And the supervisory control part, that's the brain. It lets a human operator see everything at once, on one screen, and make critical decisions or adjustments from a central location.
So this diagram here, this is your classic SCADA blueprint. Let's start over on the left in the control center. That's mission control. It's where operators are looking at what we call HMI, or human-machine interface screens, to visualize the entire process. From there, the system talks over a network to all these remote stations. And at those stations, you have these specialized industrial computers, things like PLCs and RTUs. And their job is to physically interact with the real world of pumps, valves, and sensors. And hey, see that little link on the right connecting to the enterprise network? Keep that in the back of your mind. We are definitely coming back to that.
Now, inside that control center is this really important component with a very cool name, the data historian. And its job is pretty much what it sounds like. It is the system's indestructible black box. Every single temperature reading, every pressure level, every time a valve opens or closes, it's all logged as a tag with a precise timestamp. This creates this perfect second-by-second historical record of everything that happened, which, as you can imagine, is absolutely priceless for finding trends, troubleshooting problems, or figuring out what went wrong after an incident.
Okay, so we have a central brain, and we have all these remote field devices. But how in the world do they talk to each other when they're separated by hundreds or even thousands of miles? Well, that brings us to our next piece of the puzzle, the absolutely crucial role of telemetry.
Telemetry is really just the science of sending data over really long distances. And as you can see from this image, there's no single solution. It all depends on the situation. A remote station that's fairly close might use a simple wireless radio link. But a super isolated one, like a pump station in the middle of nowhere, that might need a satellite connection. Other sites might just piggyback on a more traditional wide area network. The technology can change, but the goal is always the same. Get that vital data back to the control center no matter what.
Now, when we talk about wireless, it's really a game of scale, and these two technologies here really highlight that difference. On the one hand, at a really small scale, you've got something like Zigbee. It's super low power, short range, and it's perfect for what we call a personal area network. So think connecting all the sensors and smart devices in a single room or a home. Then on the other end of the spectrum, you have WiMAX, which is designed to provide high-speed wireless access across an entire city. Totally different tools for totally different jobs.
And you can see that difference in scale perfectly right here. Over on the left, Zigbee is creating this little local web, this mesh network, connecting your thermostat, your smart meter, your security system, all inside a single house. But on the right, that one WiMAX tower is blanketing an entire town with connectivity. It's literally the difference between connecting a building and connecting a city.
All right, that's enough theory for now. Let's see how all this stuff actually comes together in one of the most complex and critical SCADA applications on the planet, a modern electrical smart grid.
Whoa, okay, I know this looks like a tangled mess at first glance, and honestly, it is pretty complex. But the key is to stop seeing it as one giant network and instead see it as a system of systems. There are actually 4 distinct interconnected networks here, all working in concert to get electricity from the power plant all the way to your phone charger. So let's break down those 4 networks.
Up at the top, you have the power generation network. That's the one controlling the power plants themselves. And then you have the transmission network, which manages the massive, high-voltage power lines. Then down at the bottom, you have the customer network, which is where things like your smart meter report back to the utility. And all of that data from those three operational networks gets fed into the fourth one, the utility's own corporate data management system.
And that last part, that connection, where the gritty industrial world plugs into the clean corporate network, that is one of the biggest and, frankly, most dangerous challenges in this entire field. This is where two completely different worlds collide: operational technology, or OT, and information technology, or IT.
For decades, these two worlds were kept completely separate, on purpose, often with a physical air gap between them. On the left, you had the OT network. Its one and only job was to keep the machines running, 24/7 no matter what. Uptime is everything. Then on the right, you had the IT network, which was focused on business stuff, email, spreadsheets, databases. They had totally different goals, different equipment, and they spoke completely different languages.
But here's the thing. Today, businesses need real-time data from the factory floor to be efficient and competitive, so we have to bridge that gap. The OT network, which we now often call the ICS, or Industrial Control System Network, is connected directly to the corporate IT network, and as you can see, that critical link, that bridge, is a firewall. The upside is huge. You get this unprecedented insight into your operations. But the risk? The risk is also huge. That firewall is now a digital doorway for threats to cross from the messy world of IT into the incredibly sensitive, critical world of OT.
So how do you manage that enormous risk? How can you possibly connect these two different universes safely? Well, the industry came up with an answer: a really detailed blueprint for integration called the ISA 95 standard.
Okay, I get it. This diagram is a lot to take in at once, but the idea behind it is actually pretty elegant. ISA 95 doesn't just smash OT and IT together. Instead, it organizes absolutely everything into a logical 5-level pyramid. It defines a place and a purpose for every single device and function, from the physical motors spinning on the factory floor all the way up to the CEO's business dashboard.
Let's just walk up the pyramid real quick. At the very bottom, level 0 is the actual physical stuff, the pipes, the motors, the steel. Level 1 is the sensors and actuators that actually touch that process. Level 2 is where our SCADA and control systems live, the ones doing the automation. These bottom 3 layers, that's pure OT. Then way up at the top, level 4 is the pure IT world of business planning and logistics. But the real genius here is level 3. It's designed to be a sort of digital buffer zone, a carefully controlled and managed middle ground that lets vital information pass between the factory floor and the business office, without exposing those critical control systems to direct risk from the corporate network.
And that brings us to a huge question for the future. For decades, this structured, layered ISA 95 model has been the absolute bedrock of industrial security. But now, with the explosion of the industrial Internet of Things and cloud computing, we have devices connecting directly from the factory floor straight to the internet, completely bypassing these neat layers. The lines are getting blurrier by the second. So the really big question we have to ask ourselves is this: can this rigid, hierarchical model evolve fast enough for this new world? Or are we building a future where our most critical infrastructure is dangerously wide open?